Hello everyone. Today is the day 7 of 75 hard research challenge, and I'm going to talk about what I did yesterday. And I studied something called RoFormer, which proposed a rotary positional embedding, and they enhanced the transformer a little bit. Okay. So in the past couple of days we have been studying what is positional encodings. We studied what is absolute positional encodings, and yesterday we also studied what are the various forms of relative positional embeddings, like LLaMa is there, or what is used in transformer XL, and similarly what is used in T5 also. So in the case of absolute positional embeddings, let me go through the paper. So in the case of absolute positional embeddings, what they do is that they simply at each position I, they add the positional encoding at ith position to the content of the at the ith position, and then they pass it through a matrix W, Q, K or V, right? Uh, Now, in the case of sinusoidal embeddings, what happens is that they have given the value of pi with this particular formulation. If you want to know more about this and the various properties of sinusoidal position embedding, you can look at my previous set of videos. Okay. Yesterday we saw that there is something called relative positional embeddings, and in the case of relative positional embeddings, what you want to do is that you want to capture how far the key is from the query or the value is from the query, rather than having fixed positional encodings for each of the positions, right? So for example, in the case of transformer XL, or rather let's first see what Shaw et al did. You can find details in my previous video, but in the case of Shaw et al, what they do is that earlier we saw that they add xi with pi, that means which I is the absolute position, right? But in the case of Shaw et al, what they do is they add something called PR, where R is defined as is the difference of between the two positions M and N, where M is the position of the query and N is the position of the key and the corresponding value, right? And they also cap it with R min and R max. That means if you move very far away from your query, then all these positions are considered as either R min in on the left side or R max on the right side of the position, the query. Okay. In the case of transformer XL, we saw that you can break down the dot product or the inner product between Q, M and Kn into 4 terms. And various forms of papers have proposed various solutions to this, where they replace the absolute positions Pn and Pm, right, with their relative counterparts. For example, in the case of T5, what they do is that they keep this particular term which is independent of the position, because there is no P, only content xm and xn are used, and these three terms are dependent on the positions. So what they do is that they replace these three terms with a bias term. In the case of bias term, which is a learnable value, it is again relative. For example, you see that it is I comma j. Okay, and we saw various formulations other than this also. Okay, in the case of relative position embedding and absolute position embeddings that we have seen so far, all these were additive in nature. That means you are adding adding the positional encoding in the content, right, in one way or the another. However, in this case, which is rotary position encoding, these are multiplicative. That means you are essentially you are multiplying the positional encoding into the vectors of query and the key. Okay, so this particular section describes the proposed approach and gives you a brief introduction of what is their formulation in the section 3.2. However, it is too brief, and in most of the videos that I saw, most of them did not discuss the details of the derivation, which I feel is very critical and missing on many blog posts, etc. At least I could not find it. So I had to sit down and think about all of this. So I'm going to go through that first, rather than rather than simply telling you what their formulation is doing. Okay, so now in the case of positional embeddings, we have PT, which tells you the absolute position at time step t, or we have PR, which tells you the relative position encoding, which is usually a d-dimensional vector, right? Where d is usually given as 512. That means it's a even number. Usually they keep it as a even number. But for the sake of simplicity, this section of theoretical explanation starts with saying that let's assume that d is equal to 2, and then we will extend it to a general case. Okay. So now in this case, what they do is that let's say that you have a query vector qm and a key vector kn. Okay, so these are represented correspondingly by fq and fk. Let's focus on qm first. So we have a query vector qm, okay, and which is represented by fq, a function which takes two arguments. First is the content at position q, second is the position at which the content is lying, that means m. Similarly, for the key vector kn, we have a function kn which takes in two arguments, the content at kth position corresponding to xk and the position at which it lies. Okay. So now they say that let's assume we have to take a dot product. I mean, that's not an assumption. We have to take a dot product between query and key. Let's assume that it is represented as a dot product, which is represented here by angular brackets between these two functions. They say that let's assume the value of this dot product can be represented using a function g, which will be a function of three arguments xm, xn, which are the the values of the content of the query, content of the key, and the difference in their position. Okay, and now this is a general equation and we have to ground it with some initial conditions. So what are those initial conditions? We say that let's assume q and k are the query and key vectors such that these are corresponding to when there is no positional encoding for the query and the key. That's what is written here, right? So I'm walking you through the paper so that if you read on your own, you can relate to what is the explanation of each and every sentence. Okay. So now, given this, we know that we go back to our high school basic mathematics of vector algebra, where a vector can be represented using like in the 2D space. For example, if this is the vector, it can be represented in the real and the imaginary x-axis, which is represented by x-axis and y-axis respectively. So this is something called the Euler's formula, right? So if you have a vector fq, xq, m, right, we have it here as qm, then it can be represented using two parts. First is the magnitude of the vector and second is the function exponential of the imaginary part of the angle between the angle of the this particular vector, right? So this is what they have written. They have written rq represents the magnitude of this vector, right, this particular vector, and which again will be a function of xq, which is the content of the query and the position of the query, and the imaginary part, which is will be based on the angle theta q, which again will be a function of the content of the query and the position of the query. Similarly, we can define the fk xk n comma n as the rk xk n, which gives you the magnitude of the vector, and this part gives you the exponential of the imaginary part iota times the angle of the vector. Similarly, you can represent g, which is the dot product of two vectors. So it can be a vector. It can be represented as a vector. Again, we represent it as a rg, which gives you the magnitude of this vector, which again will be a function. That means it will depend on xq, xk, and the difference between these two positions, right? And this is the angle corresponding to that. So far so good. This is simply we are defining some notations. We defined two vectors fq and fk and a function g such that which represents the dot product of these two vectors, right? And we have initial conditions q and k that tells you what is the vector when there is no positional encoding attached to it. And we represented it using something called a Euler's formula. Euler's or Euler's formula, whatever you prefer, whatever accent or dialect you prefer. Okay. So These are called radial. This is a typo in the paper. This should not be radical. This should be radial and angular components of Fk and Qk. Okay. So now what we can do is that let's put these values in this particular equation. Right. We have a dot product equal to G, and once we do that, we just simply equate them. Okay. So we say that when we take the dot product of this will become RQ XQ comma M into iota theta Q XQ comma M multiplied by again RK XK N and theta K XK N, which will be equal to this particular value here. Right. So that essentially means that we have RG XQ XK N minus M theta G XQ XK N minus M. I'm spelling it out or writing it out so then it becomes a little bit easier to have a detailed on that detailed derivation on that. So these are two complex numbers. When complex numbers are multiplied with each other, we usually take the complex conjugate of the second one, right? So this left hand side LHS and this is the RHS. So this left hand side will eventually turn out to be RQ, RK. Now let me write it down properly. So this will turn out to be RQ XQM into RK XKN, right? This will be the magnitude of the resulting vector after multiplication of two complex vectors or complex numbers. Then I theta K XN, apologies, XKN minus theta Q XQ comma M, right? And this is equal to RHS. So now what we can do is that, let's say, let me just copy paste this here, RHS here, that's what it is going to be equal to. Okay. So now what happens is that we simply equate the the magnitude part with the magnitude part of the LHS of the and the RHS, and similarly we say that this difference will be equal to this particular value, and that's what has been represented in the 24th equation. That means you have a product of the magnitudes equal to the magnitude of the RG and the difference of the angle equal to the final angle in the RG function. Okay. Now let's see what, so far so good. Now let's see what happens to this initial equations. Okay. So initial equations, we have Q and K. Q is a vector and we can represent Q as the real part of the vector and the angle it had initially. Initially the vector might be having some angle which is represented by theta Q, right? This is again similar to what we did here in the Euler's formulation, which again will be equal to RQ XQ at 0th position and this particular value based on this particular assumption that we made, right? Okay. So now when we equate these, so where these are radial and angular part of Q and K on the 2D plane. That's what I explained just now. Okay. Now we have this set of equations. Now let's try to solve them. So in the equation 25, now let's set M is equal to N and equation in the equation 24. That means this particular equation. Let's take the first part. We say that M and N are equal to each other. So this will lead to here also M, here also M, and M minus N will be equal to 0, right? So this particular part comes from that, from the 24th equation, right? And then you equate it to RQ XQ0 and XQ0 because That's what we saw here also, because right, that this comes from this particular equation. Once you have this, you can simply say that this becomes equal to q and k, right? Similarly, for the angle, we can do the same thing. You take the left hand side of equation 24, you equate it to the right hand side, you put m is equal to n in both the cases. This will result to m minus m being equal to 0. Now, this particular solution is also true when you have m is equal to 0 and n is equal to 0, which will eventually lead to theta k and theta q. So, what does this mean, right? This essentially means that on one hand, it says that the solution of RF could be formulated from equation 26a. That means that if we have this particular value equal to q and this particular value equal to k, then we have a solution to this equation, right? So that's what they did here. Similarly, you can have the Rg value being equal to this particular number, which again comes out to be the product of this. Now, what does this mean? We are solving certain equations. What does this mean? This implies that Rq, the functions Rq, Rk and Rg, the final value of these are independent of the positional information, right? There is no theta q or theta k in any of these three equations, right? So that means that the magnitude of the vector, final vector, is independent of the position. Okay, we have to remember this for the future sake. Okay, now what we can do is that now we focus on equation 26b, and we see that what happens is that let's pick this part and this part. Okay, now let's rearrange by shifting theta k to the left side and theta m to the right side. So this will lead to this particular equation here, that is represented by this particular part, right? Now this also implies that the angular functions do not depend on the query and the key. So these are purely functions of the difference between the query. If you move the query from 0th position to mth position, and similarly if you move the key from 0th position to mth position, the angle movement between these two is again same, right? So we say that this is represented by a function. For example, theta q minus theta q xm comma m xq comma m minus theta k is represented by theta f x q k m minus this part, right? Okay, so now we denote this particular value as phi m. Okay, so phi m is given to us as theta f x either q or k comma m minus theta q or k, right? So the distance you move when you move from 0th position to mth position, what is the change in the angle? That particular value is represented by phi m. Okay, so what does that mean? So we rearrange these two parts, right? So we say that this particular value is there. We say what is the value of this. Then for finding the value of this, we simply move this to this position, and this is what this equation number 28 is representing. This particular equation 28, right? Okay. Now in this equation, in the equation 24, right? That is the equation that we saw here. Let's put n is equal to m plus 1. That means let's see what happens when we shift from when the query and key are just one, they move by a one position, right? So what happens is that phi m plus 1 minus phi m turns out to be this particular value. So how did we get to this? We have this particular value we computed here, right? So we put this particular value in the equation 24 in this particular lower part, and we simplify. Some of the values will cancel out, and this is what you are left with, right? So what does this mean? That means that let's analyze. So left hand side is a function of m, which is how many positions you have shifted, right? What is the position that you are currently at? But the right hand side is not a function of m. right? So that's what they have seen. Right hand side is a constant irrelevant to m, and that essentially says that independent of how much you move, if you move by 1 point, right, if you move from by one position, that means you start with m and you move by one position m plus 1, then the angle by which you move is independent of the initial position that you were in. Okay, so what does that mean? That means that if you are at position m, I am repeating it again, and you move by one position m plus 1, then the angle by which the vector will rotate in the polar coordinates is independent of what the initial value of m was, right? So if you move from 10th position to 11th, or you move from 100th position to 101st position, the amount of angle shift is constant. So now you can, maybe you can see that where is the relative part coming into picture, right? In the relative positional embedding that we saw earlier, that is additive relative positioning, what we did is that if you move by 4 positions, we simply take a difference between m minus m, right, in the case of LLaMa, etc., right? So that remains always constant. So similarly, in this case, they say that our angle shift remains constant, and as you keep on moving from, let's say, position m to m plus 1, then m plus 2, m plus 3, and m plus 4, this will simply form an arithmetic progression, right, AP, and which is short form for AP, and we can represent it using phi m is equal to m theta plus gamma, right? You simply jump by a particular number, right, always independent of where you start from, right? So similarly, what we can do is that now we can represent FQ, and we can put in the values, and we get the magnitude of Q into e raised to power iota theta q m theta plus gamma, right? So what does that mean? That means that you had initial vector with you, which is now formulated as q here, and you move it by an value by the angle of m theta. Okay, similarly you do it for k. In their work they assumed that gamma is equal to 0. Okay, so this is the equation that comes out to be. Okay, so now from here to here, what they did is that they simply said that because we did not assume what was the initial value of q, so it was treated as a general vector without loss of generality. So they say that we simply assume that our q vector and k vector are given by these formulas, which is simply you do a linear transformation of the content at m and content at n. I think there is a typo here also. This should be xm and this should be xn. This is correct. This is probably wrong, but maybe leave a comment if I am thinking incorrectly. Okay, then we simply said gamma is equal to 0, and this is the equation that we get. Okay, so now stare at this. Let's just stare at this equation. What is this equation saying? That if you want to represent a vector xm at a query vector xm at position m, then you simply take the xm, that means the initial information or component xm, do a linear transformation using the matrix wq, and shift the angle of the vector by m times the original angle. So let's draw it a little bit. So that says that, let's say you had a vector like this. Okay, let's now the magnitude of this vector is given by wq xm, and the angle is, let's say, given by theta. Now this is at position, whatever position, let's say a 0th position. That means the vector is given to you independent of the current position. Now let's say the vector, so let's say there is a sequence of sentence, like a sequence of tokens represented as by a sentence. Now let's say you had this vector q, I'm representing using a vector. This q vector now is to be placed at position m. Okay, so this content is to be placed at position m. So what you do is that you transfer this vector, rotate this vector by an angle of m theta. Let's say it reaches this particular value. Let me draw it in a different color. So you rotate this vector by an angle of m theta. So now the new angle of this vector will be this, but the real part the magnitude part remains the same. That means this. Okay, so that's what we are going, that's what this particular equation is denoting. Now let's go back to a beautiful image that you have shown. That's what I have also shown. That let's say you have a vector here, original vector, content vector. Now you want to place this content vector at mth position. You simply rotate it by the angle m theta 1. Okay, so this was the case for two-dimensional embedding when we had the position given to us, position vector given to us in where d is equal to 2. So what do we do in the case when we have a larger matrix with us, right? So let's first focus on before we go to that, this is the formulation that we saw, that you have fq given as this particular formula, fk given, and gk is similarly given as this formula. Now what you can do is that you can represent this rotation by using a rotation matrix. Okay, what does that mean? That means let's say you have you have this particular rotation matrix with you that essentially says that you multiply this particular value with the weight matrix, which is in turn multiplied with the input content at mth position. This will lead to this particular equation. This is a standard formula for the rotation matrix. Okay, so please ignore this particular part. I have written it for some other reason, but I think I don't even recall why I wrote this. Okay, now in the case of general formulation where you have a d-dimensional vector, let's say for 512, what you do is that you have this rotation matrix with you, but it was in the 2D form. You copy paste it, you create a larger vector where every 2 dimensions will be rotated at a time. Okay, so that's what they showed in the figure also, that at a time you pick the 2 dimension, you rotate them and paste them back. Next time you pick the next 2 dimension, rotate them and pick them up if you rotate it by m, right? So you rotate, if you have a d-dimensional vector, if you have a d-dimensional vector with you, then at a time you rotate the first 2 dimensions, first and second and third and fourth and so on and so forth, right? Okay, so for that they formulate the rotation matrix in this form, and this is a very sparse matrix because this is very close to the diagonal. This is more or less similar to a diagonal matrix. A lot of sparsity is there. For example, in the case of 512, it will be extremely sparse, right? So they show a very clean implementation of that, where they simply say that you can represent this particular rotation matrix in the form of these two particular point-wise multiplications, Hadamard product, and a simple addition. This is very straightforward, and this, when you multiply them together, this leads to a very it leads to the same equation that we formulated. So that's all for today. Thanks for watching. Tomorrow I'll be talking probably about DPO, because that's what I finished today. Okay, thanks for watching.